Hello, everyone, and welcome back. 2 lectures ago, we introduced vector spaces. And in particular, we saw that the space of continuous functions on a given domain, say D, is itself a vector space. Now, this is pretty easy to understand. It says that we can take 2 continuous functions and add them together and get another continuous function. And there's all kinds of these other axioms that can be satisfied for vector spaces, but it's a fairly intuitive concept. The idea here is now that we've lifted ourselves up a level of abstraction, and we have a whole space of functions that we can choose from. And these are continuous functions on a given domain. This is like how I say, choose a real number, let X be in R, or choose a rational number, let X be in Q. Now, what we saw in the previous lecture was that we can use this idea of having a space of continuous functions, this large infinite dimensional space, as we proved, and we can do the same things that we were doing, say, with real numbers at the beginning of this lecture series. And that is ask ourselves about sequences of functions. Now, what we saw in the previous lecture is that sequences of functions become slightly more complex. There are 2 different ways that these things can converge. They can converge pointwise. That means you put a value of X in and you track it across the sequence and you ask if that sequence of real numbers converges. Or you have uniform convergence, where you say that the difference between your sequence and its limit over the entire domain, so in the sup-norm, the uniform norm, is going to 0. Now what we're going to do is we're going to continue to work with that high level of abstraction, those vector spaces, and we're going to ask ourselves, when do sequences actually converge? And this is going to lead us to a discussion of what are called Banach spaces. Now, these are named after the mathematician Stefan Banach. And in particular, what we're going to see is that our space of continuous functions, in particular on a closed interval, is not only a vector space, it's not only a normed vector space, but it's a Banach space. So now you might have the big question mark of what is actually a Banach space? That's what we'll start with. That'll be the first definition that we present for this lecture. Okay, so definition. So in a vector space V, equipped with a norm, so remember what we already defined what a norm is, right? It's a way of sort of measuring distances in this abstract space. Well, we say that a sequence V sub n of elements in V converges to V, and this means in norm, if and only if the distance as measured by the norm of these 2 things goes to 0 as n goes to infinity. So this is just an abstract way of talking about when sequences converge in a vector space. Remember, with the real numbers, we saw that the norm is the absolute value. So this makes sense. This is consistent with what we've already seen with the real number system. Then we call a sequence Cauchy. So remember, we introduced what a Cauchy sequence was. Well, let's say a Cauchy sequence, sorry. We introduced what this is for the real number system. Now we're just going to abstract this, and it's going to be the same definition with absolute values replaced by norms. So this is a Cauchy sequence if and only if for all epsilon greater than 0, there exists some capital N in the natural numbers such that if you look at anything beyond this capital N, this implies that the distance between these elements of the sequence, so Vn and Vm, is less than epsilon. Now, go back and look at the definition of Cauchy sequences that I gave you for real numbers. It's exactly the same. The only difference here is that now I have a norm instead of the absolute value and say V's instead of X's. Okay, let's keep going. A normed vector space, so that's just a vector space equipped with a norm, will be called complete. Again, a word that we've seen before in the context of the real numbers. So it's called complete if and only if every Cauchy sequence converges. Now, remember, we had the completeness axiom for the real numbers. That's how we constructed the real numbers from the rationals. We said that every Cauchy sequence has a limit. It converges in the real numbers. Now, in this case, we're up a level of abstraction and we say, okay, imagine you have a vector space with a norm. Then if you have a Cauchy sequence, we're going to call that thing complete if that Cauchy sequence has a limit. And this is where we arrive at the definition of a Banach space. So a complete normed vector space. So there's a lot of qualifiers on here now. We have complete, we have normed, and we have vector space. Things are starting to add up. We just now are going to introduce a shorthand for this. This thing is known as a Banach space. So as I said, this is named after the mathematician Stefan Banach, who was active, I believe, in the early 20th century. And he was the first one to really develop this idea, and he has a number of proofs that are associated with properties of these spaces. So he really sort of pioneered this area and sort of gave way to a lot of what we're going to talk about. Okay, so we have a lot here, right? We have the idea of convergence and norm, and then we can use that to formulate Cauchy sequences and completeness. Finally, we say a complete norm vector space. So 3 qualifiers: has to be a vector space, has to have a norm, and has to be complete. We call that thing a Banach space. Okay, let me show you a version of a theorem that we proved early on. In any normed space, normed vector space, pardon me, vector space, say V, if a sequence Vn belonging to V converges, then it is a Cauchy sequence. Now, this is exactly what I proved for the real numbers, I believe, in the second lecture of this series. So like I said, the idea of a vector space is sort of abstracting what we understand about real space, or just the real number system. The norm is abstracting what we understand about the absolute value. And so this theorem is just abstracting what we already understood about convergence in the real numbers to convergence in a general vector space. So let's do this as a nice little exercise so that we can sort of get fluent with just general vector spaces. So let's say, suppose Vn is converging to V, which from the previous definition, from the definition above, this means Vn minus V is going to 0 as n goes to infinity. And this is in the norm of the vector space V, right? So it's the norm vector space. You got the norm, it came with it. We don't have to do any work here. Now, we need to show Vn is a Cauchy sequence. Okay, well, if it's going to be a Cauchy sequence, that means that we're going to have to show something is smaller than epsilon. So let's start with an epsilon greater than 0. Then, because this thing is convergent, there exists some capital N. And again, this corresponds to epsilon. I don't write that every time, but you need to remember that. This is an important aspect, such that if I look beyond capital N in this sequence, this implies that Vn minus V is less than epsilon over 2. Remember, there's an epsilon over 2 in here. This tells me a triangle inequality is going to come up. We talked about this in the last lecture. We've seen this in numerous lectures. In fact, this proof is going to be almost identical to what we did with the real number system and absolute values. You can just go through and change all the absolute values to norms, and you'll get the same thing. So this says, hence, if n and m are greater than or equal to capital N, we have, well, okay, well, the norm of the difference between Vn and Vm, I can add and subtract V into here. So this becomes Vn minus V plus Vm minus V. Now, just like the absolute value, norms are assumed to satisfy the triangle inequality. So I get Vn minus V plus the norm of Vm minus V. Now, these things are far enough into the sequence that they are within epsilon over 2 of the limit. And you can see, again, I said epsilon over 2. That means that a triangle inequality is coming. You can see it. This gives me less than epsilon. And so this implies Vn is Cauchy. All right, so I'm running out of room on the bottom of my page here, so I just kind of stuck that in, but that shows us we have a Cauchy sequence. Okay, well, now let's just talk about an example, because we have a particular vector space we care about in this class right now. So let's remind ourselves, in the context of the definition that I just provided up here, how this applies to the vector space of continuous functions on a closed interval. So in the vector space, again, we already proved that this thing is a vector space, C of A, B. We actually proved it for general domains, but here we'll focus on just a closed interval. And this is equipped with the sup norm. The sup norm, we say Fn converges to F in the norm if and only if the sup norm between these two things goes to 0. So that is uniform convergence. So we've already spoken about this in the previous lecture. This is the convergence that you're getting in the space, in the vector space, the norm vector space of continuous functions on a closed interval. Now, of course, this naturally lends itself to the notion of Cauchy, because you're just going to have Fn minus Fm in the sup norm. And therefore, you can ask the question if this thing is a Banach space. Now, of course, the title of this video is the Banach space C of AB. So you know already that this thing is going to be complete, but that's going to be what we're going to prove with the following theorem. So the vector space C of AB equipped with the norm, with the sup norm, pardon me, equipped with the sup norm is a complete normed vector space, i.e. a Banach space. Now, we have already shown that this thing is a normed vector space, right? We already showed that it's a vector space. Then on top of that, we showed the sup norm is itself a norm. So now the only thing that we need to do is we need to show that Cauchy sequences actually converge. So that gives us a nice criterion of this space. It tells us when sequences are going to converge. If we can show that a sequence is Cauchy, then it has to converge. So let us suppose Fn is a Cauchy sequence. Now remember, for this thing to be a complete space, this thing has to have a limit. So it's a Cauchy sequence. And we are always talking about the sup norm here. So then we need to prove that there exists some function that is continuous on AB such that Fn converges to F uniformly, right? So in this space CAB, in its norm, in the sup norm. All right, so we're dealing with convergence. That means let epsilon be greater than 0, always. Then there exists some capital N such that if I look at n greater than or equal to m, which is greater than or equal to capital N, this implies that Fn minus Fm in the sup norm is less than epsilon over 2. Okay, so this is just coming from the fact that we have a Cauchy sequence. Now, for each fixed x in AB, so we're going to show pointwise convergence first. So for each fixed x, then we've done this trick many, many, many times. If you do this evaluation at the single value x, you ask yourself, what is the difference between Fn and Fm at this point? Well, this thing is less than or equal to the maximal distance as measured by the sup norm, just from the definition of the sup norm, which is less than epsilon over 2. But that means that the difference between Fn of x and Fm of x can be as small as you want it, because epsilon was as small as I wanted it to be. Thus, for all x in AB, this is showing us the sequence Fn of x, so measuring the sequence evaluated at the same value of x, hopping along, is a Cauchy sequence. Of real numbers. That's the important piece here, right? Now, we know that with a Cauchy sequence of real numbers, there exists a limit. So by the completeness axiom, Fn of x must converge. Again, this is pointwise convergence. I haven't shown uniform convergence yet. So let's define f of x by f of x is equal to the limit as n goes to infinity of Fn of x for all x in AB. So I've given this general function captures the limit of each one of the Cauchy sequences Fn of x as n goes to infinity. We don't know if this thing is continuous yet, but that's what we are going to show. So now let's go to a new page so that we have lots of room to work with. So now for all n and m greater than or equal to n, we have Fn of x minus Fm of x is less than epsilon over 2. And holding, so I'm going to do this a little informally. So holding x fixed in AB. Okay, so I just imagine x is fixed for a second and let m go to infinity. Then we find, so you can do this more rigorously if you'd like, but I'm going to do this slightly informally because it just makes notation a little easier. And we've seen this already, right? These inequalities get passed over to the limit as well. So in this case, Fn minus its limit point is within epsilon over 2. But since this works, for all x in AB, we have that the sup norm of Fn minus F is less than or equal to epsilon over 2 which is less than epsilon. So why is that the case? Well, this fn of x minus f of x, this holds for all n greater than or equal to n, capital N, and every x in the interval. And so therefore the maximal difference between fn of x and f of x over all x's is less than or equal to epsilon over 2. So therefore that's exactly what the sup norm is quantifying. It's asking for the maximal difference. So that's less than or equal to epsilon over 2, which is less than epsilon. And so fn converges to f uniformly on AB. And from what we proved in the last lecture, this implies f is also continuous on that space. And therefore, we see that Cauchy sequences of continuous functions on a closed interval will therefore have a limit in that space. All right, that limit is continuous, and you converge to it uniformly, much stronger than pointwise. Okay, so in the previous lecture, we played around with these notions of pointwise convergence and uniform convergence. And one of the things that we saw was that you have pointwise convergence in many cases leads to a discontinuous limit. And that's how you can sort of rule out that it's not uniform. So there's a sort of natural question one can ask. What if my limit is continuous? Is it going to be the case that my sequence converges uniformly in this case? And the answer here is again, no. So let me give you another example, right? So this is a very, very delicate process, this trade-off between pointwise convergence and uniform convergence. So this is, highly nuanced material that I really, really want you to pay attention to and focus on, what these examples are really showing you about these types of convergences and what they say about this big space C of AB. We define a sequence Fn of C0, 1. Okay, so I picked A is equal to 0, B is equal to 1. For all, I'm going to start counting at 2, and you'll see why, as follows. Okay, Fn of x is going to be equal to, so it's going to be piecewise defined, it's going to be n times x if 0 is less than or equal to x, which is less than or equal to 1 over n. It's going to be 2 minus n times x if 1 over n is less than x, which is less than or equal to 2 over n. And it's going to be 0 if 2 over n is less than x, which is less than or equal to 1. And this thing is pretty easy to plot. It's just like a little triangle hump function. So let's see, here's my x-axis. My function, actually, let's straighten up some lines. Just going to look like so. So nothing fancy. This is, let's put this maybe in green so it pops out a little bit. Here's 2 over n. Here is 1 over n. This thing always has a maximum at 1. And this is my little piecewise defined function, Fn of x, right? So you can see that the location of the hump is moving closer to 0 as n gets large, but the height of that hump is always at 1. Okay, so clearly, so some convergence. So let's talk about pointwise convergence first, okay? So pointwise convergence. So x is equal to 0. Well, in this case, Fn of 0 is equal to 0 for every n, which clearly goes to 0. It's a constant sequence of zeros. So at x equal to 0, you converge to 0 pointwise. Now, if x is between 0 and 1, with 1 included, then in this case, so you are in the cases of nx, 2 minus nx, or 0, depending on where you are in that interval and depending on what the value of n is. But here's the important piece. So there exists some capital N such that, so if X is fixed, well, if N is large enough, this implies, so this is just the Archimedean property, 2 over N is less than X. Okay, so you pick a value of X, maybe it's 1 over pi, whatever the number is. Well, then I can always find, for that X fixed, I can find an N large enough so that 2 over N is smaller than it. Again, just the Archimedean property. So this implies that Fn of X is equal to 0 for all N greater than or equal to N, because we are in this third case of the function right here, right? So eventually the hump has moved so close to 0 that you have lost yourself. Maybe you're over here in the 0 range. So this implies that Fn of X is an eventually constant sequence. So it converges to 0 as n goes to infinity for all X in 0 to 1. Okay, so what does that mean? It means for every fixed X, my function converges to 0. So therefore, Fn converges to 0 pointwise as n goes to infinity. Now, the constant function 0 is itself a continuous function. So let's put that note here. This is continuous on 0, 1. So I have pointwise convergence to a continuous function. So is the convergence uniform? Right, so we're in a completely uncharted territory compared to what we talked about in the previous lecture, because in this case, pointwise convergence gives me a continuous function. It's 0, but it's still continuous. So the natural question is, the sort of naive interpretation here would be, well, this thing has to be uniform convergence. Well, let's look at it. But if I look at Fn minus 0 in the sup-norm, this is really just asking me what is the maximal value of Fn, which, let's take a look at my picture. I said the peak of my triangle is always at 1. So that means that the maximal value here is 1 for every single n, which converges to 1 as n goes to infinity, which clearly does not go to 0, which implies that Fn does not converge to 0 uniformly as n goes to infinity. So that's an important piece, right? You can still get pointwise convergence to a continuous limit, and you still won't necessarily have a uniform convergence of your function. So, okay, maybe you're annoyed with this. You're just thinking like, Jason, all you do is give me counterexamples, right? When is something going to actually work? Well, we can thank Dini, another mathematician, 1800s mathematician, Italian, for the following theorem, which helps us understand when we can transfer pointwise convergence over to actual uniform convergence. So again, as I said, this is due to Dini. So let's give him some credit on this one. So let's say, suppose we have a sequence of continuous functions in the Banach space, the continuous functions on the closed interval for all n greater than or equal to 1. And suppose that Fn of X converges to f of X at least pointwise, on AB, where f is continuous as well. Okay, so there's a little bit of work that needs to be done if you want to apply this. You have to first establish pointwise convergence to a continuous function. Then we can say if for each X in AB, so for every point, the sequence of numbers so the pointwise sequence of numbers Fn of X is monotone. Remember, monotone means either increasing or decreasing. So it's monotone increasing or decreasing. Increasing or decreasing. Then we can guarantee that we have uniform convergence to F as well. So uniformly on AB. Okay, so what this tells you is that if you have pointwise convergence to a continuous function, as we saw with the previous example right here, that's not enough to tell you that you actually have uniform convergence. What Dini says is if you can show that that pointwise convergence is also monotone increasing or decreasing, then you have uniform convergence. Okay, so this is very, very particular, but let's take a look at how this is done. In our proof, we're just going to focus on decreasing. Increasing is done in the same way. So let us suppose Fn of x is decreasing. So this is a decreasing sequence. Converging to f of x as n goes to infinity. Sorry, for all x in AB. Okay, so if you want to do this for increasing, try and do that as an exercise. It should be very, very, very similar. So we want to show that Fn converges to F uniformly, which is the same as saying that Fn minus F in the sup norm goes to 0 as n goes to infinity here. That's what we want. Okay, we know that F exists. We know it's continuous. So let's start fresh on a new page and let's start defining some pieces. So let's denote H sub n is equal to Fn minus F. Okay, so this is going to be the difference between the sequence elements and its limits. Now we know pointwise this thing goes to 0. And also this is a difference of continuous functions. So this thing is a continuous function on AB. And this is for all n greater than or equal to 1. Also, for all x in AB, Hn of x is a decreasing sequence. It's actually a decreasing null sequence. So a decreasing sequence of positive numbers approaching 0. Okay, so this is important, right? So this is again just quantifying that pointwise convergence that we had. Now, I care about convergence. So how do we start every convergence problem? Let epsilon be greater than 0, right? You're tired of seeing it. Then for each fixed x in the interval AB, I can find, so there exists an n sub x, again, pointwise convergence, it means for every single x, right? Then I can find a capital N depending on x and also depending on epsilon, such that if I look in the sequence of real numbers, Fn of x, beyond some point, this implies, well, 0 is less than Hn of x. Now, this lower inequality comes from the fact that Fn minus F is positive because you're sort of decreasing into the limit. And this thing can be made smaller than epsilon over 2. Now, let's keep going. Since Hn of x, so at that point, right? So the beyond up here. So if you look at that threshold point, well, since this thing is itself continuous, Then there exists, now it's typically delta, but I'm going to call it r sub x, and you should probably guess why I'm going to call it r sub x. You probably feel like the Heine-Borel theorem might be popping up here in a moment. Such that if x prime minus x is less than r sub x, this, oh, sorry, and x prime is actually in the interval, of course. This implies, so I'm just using continuity here. Things kind of look a little ugly because there's lots of little subscripts and whatnot, but this is just continuity, so do not be intimidated by this. I can also make this difference less than epsilon over 2. Now, if I rearrange this, I have said, if I just underline this, let's do it in green so it's a little softer. Everything is smaller than epsilon over 2. And I have this inequality right here. So this tells me that 0 is less than or equal to hn of x prime, which is less than epsilon, right? So if I just put this in, this is less than epsilon over 2. And so when you bring it around down here, this whole thing becomes less, this piece that's left in there becomes less than epsilon. So just scribbling in the margins here, just so you can see where everything comes from. This is for all n greater than or equal to nx. And for, sorry, just for any x prime in there. Sorry, for any x prime in x minus rx, comma, x plus rx with x prime in AB. Sorry, just to be specific for everybody. Okay, next. Observe that. Well, I've done this for every single point in my domain, right? From pointwise convergence, I can pick every x and make this work. Well, then the entire interval belongs in the union of all of these little continuity intervals that I created, x minus rx, x plus rx. All right, so I did it for every single x, and I showed some wiggle room, and I said everybody in that wiggle room is from 0 to epsilon. And this is an open cover. Open intervals, we know that any arbitrary union of open intervals is open again. So this is an open cover of the set AB. Now, AB is a closed interval. So by the Heine-Borel theorem, you thought that we weren't going to see it again. So by the Heine-Borel theorem, there exists a finite subcover. Well, that means that I only need finitely many points to center this thing around in order to create a cover. And so this says that AB is contained in the set of k equal 1 to, let's say, little n of xk minus rxk and xk plus rxk. Right, so I only need to center each one of these intervals around finitely many points. Now, let's say capital N equal to the maximum of each one of these capital N's that were associated with each n. So this is coming from all the way back right here. So I'll underline it so you can see it. Maybe I'll put a box around it. So I only need finitely many points to care about. That means I only need finitely many of these capital N's. And so I want to pick the biggest one of them out. So such that k is equal to 1 all the way up to little n. And then let me start on the next page so we can clean this up. So that tells us that if we look in our sequence beyond this capital N that I just chose, and if x is in AB, then there exists some k from 1 to n, right? So from our finite subcover, such that x belongs to one of these continuity intervals, right? So it's an open interval, but I'm going to call it the continuity interval because it came from continuity. And n is greater than or equal to n sub x by definition, or sorry, n sub xk as well, just because it's the maximum over all capital N's. So thus, thus 0 is less than hn of x, which is less than epsilon, because it belongs to this set. Remember, this is what we did back here with this implies symbol. So let me just underline it maybe in blue so it sticks out to you. It's this thing right here. And and since hn is in the continuous functions on AB, we have, well, since this works for every single value of x and you have a continuous function, then you have this, the sup norm of hn minus 0. So we're going to show that thing, well, this is just the sup norm of hn, which is smaller than epsilon, because every value of hn is positive and smaller than epsilon. But thus, hn equal to fn minus f goes to 0 uniformly on AB. And that gives us the proof. Okay, so what was the crux of that proof? The crux of that proof was the Heine-Borel theorem, right? So we said that if we center around every single point, we can find this continuity radius, r sub x, so that, we can sort of control how our function behaves inside of that radius. But then the Heine-Borel theorem tells us that you actually only need to pick out finitely many points across that interval, and you can look at just the open sets generated by these finite points, right? So that is what's giving you a finite subcover here. So just to underline it, it's this thing right here. But once you have finitely many points, life is good, right? Because you can always ask, what is the maximum over finitely many points? These are things that exist. If there's only 10 of us in the room, somebody's the oldest and somebody is the youngest. But if there's infinitely many of us in the room, there might not be an oldest person, right? There could be a person who's 1, a 2, a 3, a 4, a 5-year-old, all the way up to 100, 101, 201, and it could just have no end. You could have somebody who's 1,000,001 years old. I know that that's not possible, but that's the general principle. So going from infinite to finite is really what the Heine-Borel theorem helped us to do here. And that allowed us to use continuity of each of the limiting elements in order to sort of control how big these things are and show us that the sup norm of the difference between fn and f is going to 0 as n goes to infinity. Okay, so in this lecture, we raised ourselves up another level of abstraction. We continued to talk about vector spaces, and in particular normed vector spaces, but now we focused on complete normed vector spaces, so-called Banach spaces. These Banach spaces are characterized by the fact that Cauchy sequences converge to a limit point inside your space. Now we saw that our particular example of a normed vector space that we really care about, the space of continuous functions on a closed interval, that thing is complete with respect to the sup norm. And what that tells us is that if you have a Cauchy sequence of continuous functions, then A converges and B, it converges to another continuous function.